Last episode, we covered a threat that gives you zero warning, but comes with a strange mercy built in. A gamma ray burst fires its energy in two narrow beams, like a lighthouse. Most of the galaxy simply isn't standing in the light. A supernova doesn't have that mercy. When a massive star dies, it doesn't aim. It detonates in every direction at once, releasing more energy in a few seconds than our sun will produce in its entire lifetime, and blasting that energy outward as a sphere, not a beam. If Earth happens to be close enough when that sphere passes through, there is no lucky miss. There is no direction to not be standing in. So today, we're asking the question this series was built to ask. If a star exploded close enough to actually threaten us, is there anything we could do? And the answer starts with a number that should make you feel a lot better before this video is even a minute old. Welcome back to Space Won't Win. We've deflected an asteroid, braced for a solar storm, and outlasted a burst of light that gives us no warning at all. This episode takes the scariest sounding threat in the whole series and asks it to show its work. If you haven't seen the earlier episodes, go watch those first. You'll want the context. Subscribe now, because by the end of this one, you'll understand exactly why astronomers aren't losing sleep over this, and exactly what it would take if they ever had to. Let's get into it. A supernova happens when a star far more massive than our sun runs out of fuel to hold itself up against its own gravity. The core collapses in a fraction of a second, then rebounds in a catastrophic explosion that for a few weeks can outshine every other star in its galaxy combined. It throws off two things that matter for us: a wave of high-energy radiation, gamma rays, X-rays, and cosmic rays, and, weeks or months later, a physical shell of stellar debris expanding outward at tens of thousands of miles per second. Unlike a gamma ray burst, none of this is focused into a beam. It goes everywhere, equally, the moment the star lets go. Here's the number that matters most in this entire video. Astrophysicists estimate the danger zone for a supernova sits somewhere between about 25 and 50 light-years from Earth. Inside that range, the radiation could strip away a significant portion of our ozone layer and expose the surface to lethal levels of ultraviolet light. Outside it, the effects fade fast, because radiation and light both weaken with the square of the distance. Double the distance, and you've cut the exposure to a quarter. So the question isn't really, could a supernova hurt us? It's, is anything close enough to actually do it? And right now, the honest scientific answer is reassuring. The nearest stars massive enough to go supernova, stars like Betelgeuse, roughly 640 light-years away, or Antares, over 500 light-years out, sit comfortably outside that 25 to 50 light-year danger zone. Betelgeuse could, astronomically speaking, explode at any time in the next 100,000 years, and it will be one of the most spectacular things humans have ever witnessed, visible in broad daylight, and it will not hurt us even slightly. Distance is doing all the work here. Survival, in this case, starts with the extremely comforting fact that we've already mapped the threat, and the threat isn't close. Unlike a gamma ray burst, a supernova actually gives us something to work with, because dying stars don't go quietly. In their final years, decades, or even centuries, massive stars become unstable. Their brightness fluctuates, their outer layers swell and shed material, and their internal chemistry changes in ways telescopes can detect. Astronomers already monitor known candidate stars for exactly these warning signs. It won't tell us the exact day, but it can tell us, potentially years in advance, that a particular star is approaching the end. Here's the detail almost nobody knows. When a massive star's core actually collapses, it releases a burst of nearly massless particles called neutrinos, hours before the visible light of the explosion reaches us, because neutrinos barely interact with matter and blast straight through the star, while light has to fight its way out from the core to the surface first. Underground neutrino observatories around the world are part of a real functioning early warning network called the Supernova Early Warning System, designed to detect that neutrino burst and alert astronomers within minutes, giving telescopes worldwide a heads up to turn and watch the explosion unfold in real time. For a supernova within our danger zone, that's hours of confirmed notice before the light and radiation even arrive. Not enough to evacuate a planet, but enough to be certain it's happening, and enough for the institutions that matter to start responding immediately. If a supernova ever did go off within that danger zone, the threat arrives in two separate waves, and they're not the same problem. The first wave is radiation. Gamma rays and X-rays traveling at the speed of light, arriving at the same moment as the visible flash. Just like the gamma ray burst episode, this radiation doesn't reach the ground in a lethal dose. Earth's atmosphere absorbs it. What it does do is attack the ozone layer. The same mechanism, the same slow-burning ecological crisis we covered last time. Depleted ozone, elevated UV at the surface, stressed crops and marine food chains over months and years. Not an instant. The second wave is different, and it's the one that makes a nearby supernova more dangerous than a gamma ray burst over the long run. Along with light, a supernova accelerates cosmic rays, high-energy charged particles, outward into space. These don't travel at light speed. They're slowed and scattered by magnetic fields along the way, which means they can keep arriving at Earth for centuries after the initial flash, elevating background radiation levels for generations rather than months. It's a longer, quieter tale on the same disaster, and it's part of why some researchers connect a supernova roughly 2.5 million years ago to a documented increase in Earth's background radiation levels found in ocean sediment, spread out over an extended period, rather than a single spike. So if you watched our gamma ray burst episode, the individual survival picture here will look familiar. Ozone depletion, UV exposure, stressed agriculture and fisheries. But stretched out, this isn't a multi-year crisis with a clear recovery point. It's a multi-generation elevated risk environment, layered on top of that same ozone collapse scenario in its early phase. The good news, and it's significant, because nothing within the danger zone is currently expected to go supernova on any predictable human timescale. This entire section is a what if, not a forecast. Here's the part that should genuinely reassure you. Because the ozone depletion mechanism is essentially identical to a gamma ray burst, the survival playbook is the same one we already covered. UV resilient agriculture, shade net and indoor farming, public UV index broadcasting, sun safety behavior treated as seriously as we currently treat extreme cold. None of that infrastructure needs to be reinvented for this specific threat. It needs to exist for any threat that damages the ozone layer, supernova or otherwise, and building it once covers both. What's genuinely new here is the multi-generational cosmic ray tail. That calls for something we don't currently do at scale. Long-term background radiation monitoring, similar to the networks already used near nuclear facilities, expanded to a civilizational level and maintained for decades. Elevated cosmic ray exposure over centuries would modestly raise cancer risk and mutation rates across the population. Not an acute crisis, but a slow, statistical one, the kind of problem public health systems are actually good at managing once they know it's there. Knowing the exposure level is most of the battle. From there, it becomes a long-term monitoring and healthcare planning problem, not a survival-in-the-moment problem. And that's really the through line of surviving a threat measured in centuries instead of seconds. It stops being about any one person's actions and becomes about whether our institutions, public health systems, agricultural infrastructure, environmental monitoring are built to function for generations, not just election cycles or fiscal years. It's the same seed vaults, the same shielded archives, the same decentralized food systems from the asteroid episode, just held in place for far longer than any of us will be alive to see finished. The ozone depletion piece of this recovers on the same timeline as a gamma ray burst, years to a couple of decades, because the underlying atmospheric chemistry is identical. The cosmic ray tail fades more slowly as the particles disperse and weaken across the galaxy over centuries, gradually returning background radiation to normal levels. It's a genuinely long recovery by human standards. It is not a permanent one. Earth has almost certainly absorbed supernova exposure like this before in its geological past, and clearly kept going. We're here, having this conversation. As proof of that 2.5 million year old radiation signature we mentioned earlier isn't a warning about the future. It's evidence about the past. Life on Earth, including our own genus, made it through whatever that event was. That doesn't mean it would be pleasant to live through. It means the honest, scientific baseline for this threat, even at its worst plausible version, points toward difficult and long. rather than extinction. So here's what makes this episode different from every other one in the series. A supernova is, on paper, the single most violent event we've covered. More total energy released than an asteroid, a solar storm, and a gamma-ray burst combined. And it's also, right now, the threat we should worry about the least. Because nothing capable of hurting us is anywhere close enough to do it. And we're already watching the ones that could matter for exactly the warning signs that would tell us decades in advance. That's the real lesson of this whole series, stacked up across 4 episodes. It was never about being fearless in the face of space. It was about knowing which threats deserve a bunker, which deserve 15 minutes of preparation, and which deserve nothing more than a really good telescope and the patience to keep watching. Space keeps throwing everything it has at us. We keep finding out we had more of an answer than we thought. So there it is. The loudest explosion in this entire series turned out to be the one we're the least likely to ever face. And the one we're already watching for. Did this one scare you less than you expected going in? Let me know in the comments. And in the next episode, we're covering something with the opposite problem. A threat that gives off no light, no flash, no radiation burst to detect it all. A rogue black hole, drifting silently through the galaxy, completely invisible, until its gravity starts bending everything around it. If you can't see it, can't detect it, and can't predict where it's going, is there anything left to actually survive? Subscribe so you don't miss it. Space won't win.